My name is Vrieze and I'm Associate Professor at the Faculty of Bioscience Engineering. I focus on the architecture of microbial ecology and engineering, and in this research I basically use mixed microbial communities or microbiomes for the valorization of organic waste streams towards different renewable products that we can then use in the bio-based circular economy of our present society. Now we live currently in an era in which we all are aware of the problems of global change. Global change leads indeed to, for example, the loss of genetic diversity, which you can see in plants and animals, etc. Now what people are less aware of is the fact that there is not only global change, but due to human activity there's also a huge input of reactive nitrogen and reactive phosphorus, so phosphate and nitrate, into the environment. And by introducing these compounds into the environment, we put a huge pressure on our natural ecosystems, being oceans, being land, as we also see more and more popping up in the media these days, the so-called nitrogen crisis. Now it's important to consider the fact that we can, and this is one of the focuses of my research, in which I will recover these nutrients, these nitrogen and phosphorus, thus preventing them from ending into the environment. And how we can do that is a research focus in which I will consider waste, in this example food waste, but this can be any type of organic waste. I will use microbial processes to convert that food waste to a range of steps into what we call microbial protein as a novel source of food, or to a lesser extent feed. Now it all starts with the process of what we call anaerobic digestion. And anaerobic digestion is a microbial process relying on mixed microbial communities that allow the conversion of a complex organic waste stream into several steps into biogas. Biogas is a mixture of two main compounds, be it CO2, which is of lesser value, but especially methane. Methane, which is very energy dense and which can, for example, be used as a replacement of fossil fuels, of natural gas. We can use it as so-called biomethane for renewable energy purposes. And this we do at present already in full-scale installations, but it still requires several research projects to further optimize the process and to focus on novel waste streams. And this is an important aspect, the novel waste streams, novel feedstocks of my research, but also the fact that we do not only focus on the production of the biogas, because these feedstocks contain so much more than only the carbon that is converted to biogas, but also contain nitrogen and phosphorus, be those elements that we also want to recover. So that's also part that we focus on in the concept of resource recovery. And then also the upgrading of this biogas to biomethane that can then directly be used as a fuel for example, also vehicles. And this all fits within the concept of the so-called biorefinery, where we do not consider waste streams, but we actually consider them as secondary resources that we can valorize. Now this process is being carried out by a range of microorganisms, a mixture of microorganisms that we call a microbiome. And we should know that when we look at the world of organisms in general, so all organisms on the planet, there's three what we call domains of life. There's the archaea, there's the bacteria, and there's the eukarya. Basically meaning the archaea are the so-called ancient microorganisms. Eukarya is the group to which plants and animals, also humans, belong, and bacteria are also single-celled microorganisms. Why is this important? Because the ability to produce methane is at present, as far as we know, exclusively contained within the domain of the archaea, and these are the so-called methanogens. For example, what you see here is an example of Methanosarcina. Methanosarcina is an important methanogen that grows in clumps, as you see in this image, and that can convert acetic acid, basically, to methane. And we study that microorganism in pure cultures, as you see here, growing it in this image, and then that way we can use this information to steer the anaerobic digestion process towards as much methane as possible by changing operational conditions. Well, let me briefly show you how that works in the lab. So this is basically how the setup looks in the lab. So what we do is we mix an inoculum, which is a mixed microbial community already from a working digester containing all necessary microorganisms. We mix it with the waste stream that we want to valorize, that we want to convert to biogas. So basically you put that then in these specific bottles, and then under the anaerobic conditions, so the absence of oxygen, biogas is being produced, which flows through these tubes and is then finally collected in the big liquid tubes. So this volume then increases in function over time, and then we can collect that biogas and perform any type of analysis on it. Now here specifically in this example, we are treating, or we are performing research on aquaculture waste streams, so basically aquaculture sludge, from which we want to know the amount of biogas we can get from. So what we do then is we apply specific additives, but we can also change pH, we can also change other operational conditions to maximize the process, thus achieving as much as biogas as possible. Now the point is, once we have that biogas, we can do all sorts of things with it. We can burn it for the recovery of energy, we can put it in what we call combined heat and power unit to produce even electricity, but we can also use it to make food. Now let me take a step back there. What we need on the planet is a lot of food, especially also proteins. And when we look at the first generation of proteins, that is animal products. Animal products, for example meat, for example milk, eggs, these are things that we use as conventional protein source. We know them, they are established in our society, but unfortunately they come at the cost of a huge impact on our environment. Which is why, let's say the last decades, we evolved to the so-called second generation of proteins, which is soy. Soy that is being produced on a large scale now, for example in South America, and which we all know already in several of our food products. Also being used as feed for animals, but the downside also here that it also has a huge impact on the natural environment. For example, what you see is in South America, where we have a huge production or huge deforestation due to the production of soy. Which brings me to the third generation of microbial protein, or third generation, which is microbial protein, where we can use microorganisms to produce food. And this starts then with the production of biogas, as we know, the production of biogas from our waste stream. And that biogas, especially the methane, we're then going to use to grow specific microorganisms. Specific microorganisms, like for example, these are methanotrophs. Methanotrophs that are microorganisms that use methane as carbon source to produce microbial biomass, and this microbial biomass is rich in protein. We can then also recover the nitrogen from the anaerobic digestion process and then put that in our production of microbial protein. And finally, we end up with a product that is microbial protein, which you see here a clear powder of, that we can finally use to put into the food chain. So to sum up my research focus, I work on mixed microbial communities or microbiomes for the valorization of organic waste streams to renewable products. And the idea is that I do this through integrated resource recovery, meaning I will not only focus on specific targets, but I will focus on different elements, be it not only carbon, but also like nitrogen and phosphorus. Important there is that methane is a central molecule in my research because it is the end product of anaerobic digestion that we can use for different applications, amongst others the production of microbial protein, and thus we can make multiple renewable resources from organic waste. And if there's any further questions that you'll have on anaerobic digestion, the production of methane, or the valorization of methane, you can of course always contact me.